All right, calculus class. So the first part of this section on partial fractions is just having you review the process. You have seen this at some point in your mathematical career, but typically when you get it to it in calculus 2, it's been a while. So what we are doing here is breaking this thing down into the fractions that were combined to give us the rational expression that we're working with. And the way that it works is, as long as this is x to the first, if I multiply this out, I'd have an x squared. As long as the numerator's degree 1 here, is smaller than the denominator's degree, which is degree 2 here, then you can use decomposition. If it's not, you have to do long division before you start the process. But because this is a smaller degree than this, when I break it down, the same thing's going to happen, meaning this is degree 1, so the numerator has to be a smaller degree. Well, smaller than degree 1 would be degree 0, which would be constants. So this numerator would have to be a constant that we don't know. This one would also. So there's the form of the decomposition, and then we need to figure out what a and b are. So what we're going to do is multiply both sides by that common denominator that we started with. And what that's going to do is, on the left side, it's always just going to give you the numerator. So you will 100%, you could just jump into that step if you wanted to, just rewrite the numerator on that left side. But on the right side, only one of these is going to cancel for each fraction. So we're going to get a times the other denominator plus b times a's denominator, because not the entire thing doesn't cancel now. Now we distribute through, we get ax plus 3a and bx plus 7b. Now it may not look like we have anything that we can do here, but to help you see it, I'm going to group the x's together and group the non-x's together, which would be constant terms together. And what I want you to see is, whatever this is, whatever a and b were, they have to add to 17x. So maybe it's like 5x and 12x. We don't know, but we know they have to add to 17. So what we do know is that a and b have to sum to the number in front of x on the other side. So we get this equation that a plus b must equal 17. And then likewise, we know that when we triple a and add 7 times b, we get 83. So we get this equation. And what we end up with is a system of equations to solve. Now, I don't care how you solve the system of equations. I do need to see, though, your work in setting up the system of equations. Personally, if this were me and I was given free rein to solve this any method I want to, I would use Desmos's matrix calculator, which looks like this. It's a very, very basic looking calculator, right? Click on a new matrix, tell it that we have 2 rows with 3 columns, right? 2 rows, that's the 2 equations. 3 columns is the a, the b, and the constants. So what we're going to do is we're going to put the coefficients of the left side, the a and the b. So there's one a, there's one b, and then the constant that they're equal to, which in this case is 17. And then the other equation, we have 3, 7, and 83. So there's that matrix. And once I have that, I'm going to press right underneath where it says new matrix. It's got the names of the matrices, and then it has, this is the one that you're going to use, RREF, matrix A, and it tells me over here to the side what A and B are. So A is 9, B is 8. All right, and I would just, just so I'll know what you did, just make a little note, RREF or Desmos matrix, something like that, just to let me know how you solved it. But get to the setup, get this equation that leads to this system of equations, and then solve the system via technology if you want to. Okay, that is a perfectly fine use of technology that I do allow for this course. Now, what does that mean? That means, if you go back to what we started with, now we know that A is equal to 9 and B is equal to 8. So why does that help us? Well, for this course, maybe I had something like this. And that would be a very difficult integral to even begin to do. I could break it apart into 2 integrals. There's, because I have sum in the numerator, but in this particular case, factoring, which this would be the factored form, would lead to that, which leads to 2 separate integrals now that I could break it down into. And both of these could be done via a substitution. They're both logarithmic. So I end up with the log of those denominators with those numerators multiplied in. So it gives us a procedure to come up with a very easy integral to do once we break this down into its partial fraction decomposition. So that's why we're going to use it. But these first questions are just having you find the decomposition. You're not going to actually do the integration yet on the first couple of these.